Part of the balancing equation process deals with can you balance an equation by looking at the actual particle diagrams. Back when we did balancing equations, I did show you one problem. If you want to go back and look at that, I think it was letter C of one of our example problems in this note packet. And particle diagrams, or sometimes we call them particulate diagrams, same thing. Basically, can you visualize what those atoms or molecules look like in terms of balancing the equation, in terms of is everything the same on both sides, etc. So the two types of particle diagrams you should be familiar with are those ion dipole forces, which again, we've already talked about. And then also being able to, number two, being able to look at a chemical reaction. Are all the reactants correct and all of the products correct, especially when you're dealing with something like a solution. So let's look at the first example here. Number one, the diagram of a soluble ionic compound in water with the ions separated. Okay. So in the first unit, or in unit 2, excuse me, we drew LiCl. So now we understand why. Okay, LiCl is a soluble ionic compound because it has an alkali metal in it. So that means that anytime you put it into water, the water is able to use those ion dipole forces to pull the lithium ions and the chloride ions apart from each other. And so you end up with Li plus, and you end up with Cl minus, okay? And do notice that I did make the Cl minus ion bigger. If you look at the periodic table, you should be able to identify that chlorine has really three more, chlorine's valence electrons are in the third shell. Lithium with a plus charge, its valence electrons are really only in the first shell, okay? Because it lost that one electron, one valence electron it had. So chlorine is a larger ion, certainly. And yes, the reason I tell you that is because, yes, they have given points on whether the ion sizes are correct or not. So with lithium, because it has that positive charge, remember that water, it's a polar molecule where you've got the dipoles going this way and this way. So you've got the partial negative charge on the oxygen. So the oxygen, and a lot of times when they draw water, they just draw it like this, which that represents the oxygen, which again is larger than the hydrogens. So when you draw this, when you draw the waters around it, you just make sure that the oxygens are close to the lithium and the hydrogens aren't. And then on the chlorine side, same thing, put the hydrogens closer to the chlorine and make sure the oxygens are away from the chlorines, okay? And that's all you would be expected to do. Again, making sure that the size of the ions are accurate. And again, that doesn't have to be anywhere close. Just make sure that the larger one is bigger than the smaller one. And then make sure that the waters are oriented the correct way. Okay, so example 2 is now we're going to the second example of can you visualize a balanced equation thinking about the actual particles moving around and reacting with each other. So which of the following particulate diagrams best shows the formation of water vapor from hydrogen gas and oxygen gas? So first of all, before you even start looking at your answers, you should think about what is that balanced chemical equation. That's really, really helpful. So hydrogen and oxygen gas, okay? And again, don't forget about Brinkelhoff here, okay? Anytime you're thinking about any type of balanced equation, anytime any of those elements are by themselves, there's always two of them. So it's H2 plus O2, and it says it's producing water, so it's making H2O. And yes, it's really, really helpful here to balance this. So I've got two hydrogens, two oxygens, one oxygen. So I'm going to put a 2 there. So I'm going to put a 2 there. Okay, and so what this particle diagram or particulate diagram is going to show, it has to show, is that 2 hydrogens react for every 1 oxygen that reacts. And again, they need to be represented as H2 and O2. So when you start looking through the answers, hopefully you look at answers A and B and right away go, wait a minute, that's not 2 atoms put together. That's just a hydrogen atom and an oxygen atom, and they're all just separated. So right away, A is a no and B is a no, because again, those are atoms, not molecules. So just like that, we're down to 50-50. Okay. Now it comes down to, do you understand what this balanced equation represents, what that 2 versus 1 represents? You have to have 2 hydrogens for every 1 oxygen that reacts. So, for example, looking at letter C, we've got, and again, looking at sizes, you should be able to tell oxygen is definitely bigger than hydrogen is. So I see 1, 2, 3 oxygens. And if I have 3 oxygens, then I need to have 6 hydrogens. And it looks like 1, 2, 3, 4, 5, 6. Okay. And that should produce, if it's a 2 to 1, that should produce, if I had 2 hydrogens, it's going to make 6 waters. Do I have 6 waters? 1, 2, 3, 4, 5, 6. Yes, I do. I think that is the correct answer. Let me just verify with answer D. In answer D, I've got 1, 2, 3, 4, 5, 6 oxygens, 1, 2, 3, 4, 5, 6 hydrogens, and then I have 6 waters. Now, answer D could be correct if it had one more thing, because we know that, again, based on the stoichiometry of the balanced equation, we are not going to need all of these oxygens. So if our answer over here contained those 3 oxygens that didn't end up reacting, because again, once all of those hydrogens react, there's only 6 of them, 1, 2, 3, 4, 5, 6. 6 of those hydrogens are only going to react with 3 of those oxygens. So that means we are going to have 1, 2, 3 oxygen molecules left over. So if it showed those, if those were here in answer D, oh, here's the leftover oxygens here as well, then D would have been the correct response. Obviously, they can't have 2 right answers, so C is certainly the best response. Okay. Example 3, an unknown gas, D, reacts with fluorine gas to form the compound DF4 as represented by the following balanced equation. So again, we can see that 1D here is going to react with 2 fluorines to make DF4. Okay, the particulate model shown below represents the moles of particles present in the container after D and F2 have reacted in a different experiment. Assume that each particle in the diagram represents 1 mole. So again, that's 1 mole of DF4, etc. Okay. Note the box corresponding to before reaction is intentionally left blank. So don't, well, hey, why is that empty? Okay, so part A says, if the total pressure at the end of the reaction is 12 atmospheres, what is the partial pressure of DF4? So we know here that the total pressure is equal to the total number of moles times R times T over V. Okay, and so the total number of moles we have here is we literally have to count them. So how many DF4s do we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 DF4 particles, and we have 1, 2, 3, 4, 5. We have 5 F2 particles. Okay? And again, that kind of goes back to the previous problem where clearly there's some fluorine that was left over that didn't end up reacting, just like that answer in part D. So if the ratio is there's 10 DF4s for every 5 F2s, again, the total number of moles is therefore 15. So remember that one way that we can calculate the partial pressure of a gas. So to get the pressure of DF4, we can take the moles that they're asking us about. So they're asking us about DF4. So there's 10 of those over the total number of moles, which is 15. And then we just multiply that by the total pressure. So we learned that the pressure of a gas is equal to, I'm not sure what's happening there, equal to the total pressure, it says total pressure times the mole fraction. Remember we talked about mole fraction times the mole fraction of whichever one they're asking us about. Okay, so we're taking the total pressure and we're multiplying by the mole fraction of the gas in question. So this is a free response question, so you could use a calculator on this. So 12 times 10 is 120. 120 divided by 15 equals 8. So the pressure of DF4 equals 8. Now, and guys, you can use logic on this. Okay, if you end up doing it exactly the way I did, that's fine. If you get 8 atmospheres and just show how you got that work, of course, that's perfectly fine. Okay, don't just write 8 atmospheres as your answer, though. Have something to justify that answer. Okay, and then in part B, assuming only D and F2 are present in the container before the reaction, determine the number of moles of D and F2 that were present in the initial reaction mixture. So basically they're asking us, fill in that box right there. So how many, remember, obeying the law of conservation of matter, every single atom has to be accounted for. So how many of those D particles were present before we started? Well, how many of those particles do we have now? I think we already counted that, right? There were 10 DF4s, so that means we had to have 10 of those D particles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't have to draw that in there, but that is, there should be 10 10 moles of particle D, okay? And then in terms of fluorine, again, every atom has to be accounted for. So we know that we had, remember those 5 that we had left over. So there's those 5 F2s. And then how many more F2s are in there on each of those D particles? Well, there's 4, okay? So every DF4 is going to have 2 F2s. So if there's 10 DF4s, that means we got to multiply that by 10. That's 20 F2 molecules just on those in that DF4 compound. Plus we have the 5 that were left over that didn't end up being used. So how many F2s did we start with? We started with 25 F2s. So 25 moles of F2. And that is a very good particulate diagram type question. A lot of times, like in the previous question, they'll start with the before reaction and you got to figure out the after, or it's a multiple choice question like the one we saw where you just have to choose which one represents it the best. Okay, make sure that when you do have diatomic molecules like the Brinkelhoff ones, that they are represented with 2 little circles instead of just the 1.